Hello and welcome to today's lesson. It's a probability lesson on probability functions, but more exactly on discrete probability functions or discrete random variables, and as part of the statistics module for mathematical methods. Our objectives of the lesson are to represent events as discrete random variables or look at what discrete random variables are, and then use mean and variance in the context of discrete random variables and calculate values for the events. That is, we're going to set up a discrete random variable and then we're going to do some measurement of it using mean and variance. They are topics which you may have touched on beforehand, but they're going to appear a lot in future modules here as well. We're going to start off with, well, what do you know about probability theory? Because if we know the answers to the following questions, we know as much actual theory as we need to complete this unit. So for instance, what total probability must equal? Do you know what total probability must equal? And if you know what total probability must equal, do you know how to represent the probability of rolling a 4 on a dice, an odd number on a dice, a 7 on a dice, or a number less than 7 on a dice? And if you don't know the answer to these questions, you can go back and find the other general probability video on my channel. But total probability, if we go through the answers quickly, must equal 1. You will see that this is a fact that is key in answering many questions throughout probability, or unraveling how to answer questions throughout probability. And if I ask how to represent the probability of rolling a 4 on a dice, for instance, if you replace the word probability with fraction, then we can just write a fraction that represents each of these things. So how to represent the fraction of rolling a 4 on a dice? Well, that's 1 out of 6, because there only is 1 4 on a dice. An odd number on a dice? Well, there are 3 odd numbers, 1, 3, and 5. So the probability or fraction is 3 out of 6. And the probability of rolling a 7 on a dice? Well, it's impossible. There are no 7 on a single dice. So we represent impossible with the number 0, although you could write 0 out of 6. And similarly, a number less than 7 on a dice, it's impossible not to, because 1, 2, 3, 4, 5, and 6 are all on a dice, and they're all less than 7. So you can write 6 out of 6, or 1. So if we look at representing events as discrete random variables, we're going to see how x is used in this. So a discrete random variable is a phrase linked to the word probability. It is a fancy name to describe the expected outcome of events with given and known probabilities, something you'll have seen before, such as rolling a dice or tossing a coin. The values must be numerical in nature, and they must be whole numbers, i.e. discrete, hence the name discrete random variable. So it must be something that gives you either a binary outcome, or such as tossing a coin. You either get heads, you either get tails, you get a very definite value, or the answer that you get will be a whole number. Something like rolling a dice, like we've just discovered, that you get a 1, a 2, a 3, a 4, a 5, and a 6, or that you get an integer value. As you'll see in the coming chapters, we'll use notation so that we can apply the theory to all situations rather than different notation depending on the event. And this is one of the key facets a lot of time in mathematics. Rather than having a different set of notation depending on what the problem is, we use general notation so that the context that it's given in has no meaning. Whether we're rolling a dice or whether we're tossing a coin, it doesn't matter. We represent it in general notation. We use the capital letter X to describe the variable we're trying to find. Okay, so let's see how you'll normally see it represented. P of x equal to x. We've got a big X, we've got a small x. Means that the probability that the random variable is equal to a particular value. Now, you probably have written or seen written calculated probability like this already, although when I put it in a separate way that I'm going to do, it often leaves people very confused. For example, if we say that a random variable x is the act of rolling a single die and ask the same questions as beforehand. So rather than saying that the probability of rolling a 4 on a single die is 1 over 6, just like we did beforehand, we could write, instead of all those words and taking the fact that it's a dice, etc., we could write the probability that x is equal to 4, or the probability that we do our action, and it equals 4 to be 1 over 6. Similarly, rather than saying the probability of rolling less than a 7 is 1, we could say the probability that x is less than 7 is equal to 1. And that is all that notation does. So how does it work in a question? So the first thing you should calculate in every question, unless it's given to you, are the values that make up all the outcomes of the event. And this is known as a probability distribution. A fair dice is rolled, calculate the probability of getting any number as a probability distribution. So if it did this, we'd set up a table a bit like this. So the values that you can get on top of the x values are the outcomes that you can get, the small x. And in a dice, that's a 1, a 2, a 3, a 4, a 5, and a 6. When we're working out the probability of each of those values, what's the probability that when we do the event, it's equal to, well, we have a small x here, and for each value, we will write the corresponding probability of the below. So the probability of rolling a 1 is 1 over 6. The probability of rolling a 2 is 1 over 6. 3 is 1 over 6. 4 is 1 over 6. 5 is 1 over 6. And 6 is 1 over 6. We can also have written this in a more generalized sentence form. So the probability of x is equal to 1 over 6 for x equal to 1, 2, 3, 4, 5, and 6. Although I will say that this notation is less useful for you at this stage, but makes a bit more sense if I was to teach you continuous random variables, which is a future unit as well, because we generally group things together for continuous random variables in this kind of style in a table, but you'll see that going forward. Okay, so let's look at an example. We're going to look at an example in words, and then we're going to take that example and put it together into a probability distribution. So two tetrahedral dice, and a tetrahedral dice, I'll explain, has 4 faces, each numbered 1, 2, 3, 4. So it's a 4-sided dice. And the score, or the total of the 2 dice, is noted or recorded. Find the probability distribution function of x, where x is the random variable score when 2 dice are thrown and added together. So we'll draw what's called a sample space to see what the results could be. And in it, I'm going to draw all the possibilities from one dice along the top. So 1, 2, 3, 4 here. And down the side I'll do the other dice, which is 1, 2, 3, 4. And what we're going to do in the middle is see what happens when you add those two numbers together. So when I add a 1 and a 1 together, I'll get a 2. When I add a 1 and a 2 together, I'll get a 3. And you can see all the results that you can get from that. That is what's known as a sample space, and this is a very common question in GCSE where they will ask you to work out what the probabilities would be based on an event where you have to work out what the outcomes would be in the first place. So we now fill out the PDF for the events. So if I say what's the probability of getting a 2, well, you can probably see now in orange or otherwise that there are 16 possible outcomes. So previously when we were rolling the dice there were 6. In this case, until you fill out this table, you may not see that there are 16, but there are 16. And the chances of the number of times that a 2 appears, well, there's just 1. A 3 appears twice, a 4 appears 3 times, etc., etc. And we get our entire probability distribution function as we do below. And if you want to check, you can see that all of those values add up together, give you 16 over 16. Or 1, and that is the question done. So if I asked you to try this one and show you some of the difficulty that happens when we use words. So 3 fair coins are tossed, the number of heads is counted. I want to draw the sample space for the experiment, make sure you detail every outcome that you can have, and then show this as a probability distribution. And then we can show it as a probability function, which is that single sentence. Again, this last part is not that important, but I'll finish this for you as we do. Okay, sample space for this is a bit different in so much as you just have to list the outcomes rather than draw it up in a nice table. But we just want to find out how many possibilities there are. Now, whether you know something about combinatorics or not from GCSE, if you studied it, you might know how many different possibilities there are for 3 fair coins, but you can do it without knowing what you aim towards. Do it in this form, as you can see down the left hand side. List all the possibilities you can have and see how many there are, and pause the video if you want to give it a go. If you've given it a go, you'd see you can have a head, a head, and a head. If you toss 3 coins, you could have a head, and a tail. You could have a head, a tail, and a head. You could have a head, a tail, and a tail. You could have a tail, a head, and a head. You could have a tail, a head, and a tail. You could have a tail, and a head. And you could have a tail, and a tail, and a tail. Those are all the possibilities that we can have, and that is our sample space to this diagram. And I often see that people miss 1 or 2 of these out, which kind of shows you some of the reason why questions aren't often asked in this way, because if you do this part wrong, then you're a bit stuck for some of your answers. Now, you would get followed through points depending on how many you listed, but people often only get 6 of the possibilities here rather than the 8. But if I was to draw on my table, on the number, we're told that 3 fair coins are tossed and the number of heads is counted. So all we're ever looking at in each of these cases is the number of heads. So we can either have 0, 1, 2, or 3. And then we'll have the probability of each of those things. So what's the probability, or how many times were there no heads? And look down the list on the left here and see how many times there were no heads. And there was only the 1 out of the 8, which is the tails, the tails, the tails. How many times did you only get 1 head? Similarly, there were 3 times. 1, 2, 3. 2 heads. There's 1, 2, 3. And that leaves the time when there's 3 heads to beat the 3 heads at the top, which is 1/8. And that is our probability distribution, and we can answer questions based on that as it goes. If you wanted to write this in the single sentence before, you start off with the probability of x is equal to x to be broken down like this. Well, you get 1/8, a probability of 1/8 for what values? What are you getting for 0 and 3? You get the probability of 3/8 for 1 and 2, and everything else is 0. And that's the way to write that. And this notation is one that you will see more often in continuous probability functions, not in this context. So let's look at another example. Let's look at a more standard example. Why we use the maths to do this and not necessarily the language. So a discrete random variable is defined as shown in the table, and we're given the function, right? We're not told in what context. We're not told whether it's rolling a dice, because actually none of that really matters. All that we want to do is work out the probability. And we're given that there are 5 possibilities. There's a 1, a 2, a 3, a 4, and a 5. And in the bottom line, we're given some of the probabilities. So we're given the probability that a 1 happening is 0.2, a 3 happens 0.1, 4 is 0.2, and 2 and 5 are represented in letters. So we don't exactly know, but we know that the probability of getting a 5 is 3 times greater than getting that of a 2. I've got to find the value of k and complete the missing values in the table based on the value of k. To be able to do that, we have to use what must all probability add up to, and that is 1. So this bottom row down here, all these values must add up together to give you 1. So we can create an equation. 0.2 plus k plus 0.1 plus 0.2 is equal to 3, plus 3k is equal to 1. And if I tidy up grouping like terms together, I will get that 4k plus 0.5 is equal to 1. Rearranging that, bringing the 0.5 over the other side, or taking away 0.5, I'll get 4k is equal to 0.5, and then dividing by the 4 will give me the k is equal to 0.125. I can then replace my values in my table, so that instead of k we have 0.125, and instead of 5 I have 0.375, because that's 5 times 0.125. So let's look at a question, another one. So a discrete random variable has a probability distribution as shown. I've got the values that the random variable could take, so -3, -2, -1, 0, and 1. And then the probabilities that go along with those. With one of those we don't know, which is D. And I have to find out the value of D and then calculate some probabilities, which we will look at in a second. To find the value of D, I'm going to create a little equation. So 0.1 plus 0.25. Oops, I'll tidy that up. Plus 0.3 plus 0.15 plus D. And what must our probability equal? It must equal 1. If I group these together, 0.1 plus 0.25 is 0.35. 0.35 plus 0.3 is 0.65. 0.65 plus 0.15 is 0.8. And I get that 0.5, or 0.8, sorry, plus D is equal to 1. And solving that gives me D equal to 0.2. And I can replace this with a 0.2. That is part 1 done. I've got to find the probability that it's between these values, that we're going to get something between a -3 and a 0. Now be careful of the signs, because the little line underneath this value here suggests that we must include the -3 but not the 0. So you think which values that this does. So does a -3 count? It certainly does. Does a -2 count? It does. Does a -1 count? It does. Does a 0? No. And does the 1 count? No. And to get the total probability, you would add those together. So add 0.1, 0.25, and 0.3. Just like before, we'd add them together and get 0.65. Similarly, find the probability that x is equal to greater than 1, greater than -1. I'm going to, I'll write in here that this is 0.2 because it's going to be used again. X is greater than -1, so I can't include -1, but I will include the 0, and I will include the 1. Our total probability is going to be what when you add those two bits together. 0.15 and 0.2 is 0.35. So let's look at another example. A tetrahedral die has the numbers 1, 2, 3, and 4 on its faces. The die is biased in such a way that the probability of landing on a number is inversely proportional to n. For example, the probability of landing on a 3 is k over 3. So where's k the constant? Find the probability distribution for x, the number the die lands on after a single roll. And I've got to set up the probability distribution with as much information as we know. Now to be able to do this, we use the fact that the probability of landing 3 is k over 3. If that is probability for landing 3, if you use the same pattern, to get a 4, it'll be k over 4. To get a 2, it'll be k over 2. And then 1 will be k over 1. We can do the same thing as before. Now I'm going to start to use proper notation here. So the sum of all of this bottom line is equal to 1. This sum value you'll have seen and probably a bit probability beforehand, but the sum of the px of x equals the x is equal to 1. Therefore we'll get k over 1 plus k over 2 plus k over 3 plus k over 4 is equal to 1. To be able to add probability together, you take a common denominator. The common denominator for 1, 2, 3, and 4 is 12. So 1 top and bottom multiplied by 12, 2 multiply top and bottom by 6, 3 by 4, and 4 by 3. You will get that 25 over 12 times k is equal to 1. Now if you multiply by the 12, divide by the 25, or rearrange that, so multiply by the bottom number, divide by the top, you will get that k is equal to 12 over 25. And you can use your calculator to simplify down 12 over 25 divided by 1, 12 over 25 divided by 2, divided by 3, divided by 4. You will get that your probability function is like that, either in this form or in the simplified form, if it simplifies down, but it doesn't in this case. and that is the probability distribution for that. One for you to try yourself. A PDF of a discrete random variable x is given by px equal to x of k y squared, where y is equal to 0, 1, 2, 3, 4. The only reason I've used y is just so we don't have every example with x, and you get used to the fact that it must be x. It can be any letter, given that k is a constant. Right? And for this, to start off with, you will replace the y with 0, 1, 2, 3, and 4. So for y is equal to 0, the probability that x is equal to 0 will be k times 0 squared. That gives you no k. You do the same for y is equal to 1, and you'll have k times 1 squared. And 1 squared is 1, or k. Do the same for 2, do the same for 3, do the same for 4, and see that you can complete a probability distribution for that. Something like this. So 0, 1, 2, 3, and 4. And then we can do the same thing as before and know that all of this probability must equal to 1. So we create an equation. So if I add all those values together, it equal to 1. If you add 1, 4, 9, 16 together, you'll get 30. 30c is equal to 1. And I'll get the c is equal to 1 over 30. And then you're going to place c back in and get your following distribution function. With this time there will be simplified values. So 4 over 30, etc. will give you the following. Sorry, this one should be 2. You can also leave them in terms of unsimplified fractions, so you could just leave them all over 30 if you wanted to. Okay, so that's the first objective done, and this time we're going to look at mean and variance. So one of the main advantages of having a completed distribution function is we can calculate the expected value of the variable x. The expected value may not be a value which is actually possible. So much the same way as we worked out the number of sit-ups that everybody could do in the class or something like that. We might get a decimal value because to work at the mean we would add them all together and divide by how many there are. But that probably links quite well with the idea that expected value is just a statistical way of saying the average or the mean. Okay, so the expected value of the distribution is effectively the mean, and we actually work it out exactly the same way as we work out the mean from a table. Now you might think this looks like a fancy formula, but the expected value of x is the sum of x multiplied by px equal to x, or written like so. I'm going to look at an example of what that looks like. Variance is the same idea. Remember, the variance measures how spread out the data is from the mean or how varied the data is. Where would you have used standard deviation as a more common measure of this, but variance is one that's the same. And variance is a similar kind of formula, but it's a compound formula given that you have to work out two things. Now, I'll point out that e of x in this case here is just the mean, the bit that we had just worked out. So if you do these two questions, and they usually do come together, you will already in the previous question have worked out what the expected value of x is, which is squared, but you need to work out what e of x squared is. And instead of multiplying by x, you're going to multiply by x squared and get the sum. And this is also how you do it for working out standard deviation. So much like the calculation for standard deviation, you need some extra columns, and we're going to look at a standard example. So the table shows the probability distribution of x, where x is the number of TV sets for a house picked at random. So here it is. In this case, you'll see that we didn't have to work anything out, but we're going to calculate the expected value of x, or the mean, and var x, which is the variance of x. Now, if you think back to working out the mean from a table, you know that we had an x column, we had an f column, and to be able to work out the mean, You take the f column and the x column, multiply them together to get fx. And then we do the sum of this one divided by the sum of this one. And that's what we get. Well, in this case, because this, I know this is a little bit weird. We think of this as our f column and this is our x column. But the sum of this whole thing is going to be equal to 1 all the time. So we don't actually need the bottom divided by the bottom. Sorry, I've got those the wrong way around. That's your x column and that's your f column. Right? So this is really your fx column, where you just multiply these two numbers together. So 0 times 0.1, 1 times 0.75, 2 times 0.1, 3 times 0.05, and we will get this. If we were to do the sum of fx divided by the sum of f, we'd add all these together. We'd add all these together and divide one by the other one. But because in probability this middle one is always equal to 1, all we need to do for the expected value is add all these numbers together. So we add 0.75, 0.2, and 0.15. And if I do that, I get that the expected value is 1.1. If I do the same for variance, we need another row. So it's the probability of x squared. So x squared times p of x. You might want to do another row that's x squared. So take your x value and square it, and then multiply it by the p of x. And if I do that, I will get this row. Now you might remember that the standard deviation formula isn't just one thing divided by another one. But to get a of x squared, we need to sum up this row here. That'll give us 1.6. But that doesn't give us the value of var, because the value of var, or variance, is that value minus the previous value squared. So if I substitute in the values that I have, that's 1.6 minus the 1.1 from the expected value squared, and that'll give me 0.39, and that is our variance. And that is how you do the mean and the variance every time. If I did something that was a bit more complicated, I could give you an expected value, and I could give you some unknown values. Now, you will see a bit of a problem, because we have two values that we don't know. They're two different letters, so P and Q. And to be able to solve things with two unknowns, well, we need simultaneous equations. Indeed, we're going to need simultaneous equations. And we're going to make simultaneous equations based on what we know about this. And there are two things we know. The first thing we know is that all probability in this line must equal to 1. So that gives us a way to make one question. And we're also given the expected value of x is equal to 3. So we're going to write down those two equations. If I start off with the first one, the total probability equal to 1, I'll make a simple equation that's 0.1 plus p plus 0.3 plus q plus 0.2 is equal to 1. If I tidy that up, I'll have p plus q plus 0.6 is equal to 1. And rearranging that, I'll get p plus q is equal to 0.4. And there's our first proper equation. For expected value of x, I need that extra row, where we need to multiply these things together. So 1 times 0.1 gives me 0.1. 2 times p gives me 2p. 3 times 0.3 gives me 0.9. 4 times q gives me 4q. And 5 times 0.2 gives me 1. If I take this equation and rearrange it or group everything together, I will get that 2p plus 4q plus 2 is equal to 3, or 2p plus 4q is equal to 1. There are my two equations that I've got, and I can solve them simultaneously. To do this, I'm going to multiply the top equation by 2. Instead of p plus q is equal to 0.4, I'll get 2p plus 2q is equal to 0.8. And then I can take the other equation, and because the two signs are the same, we're going to subtract. When I do that, the 2p minus 2p will disappear. 2q minus 4q, or if you put the bigger numbers on top, you'll get 4q minus 2q. It'll give you 2q. 1 minus 0.8 gives you 0.2. You'll see that I've done 4 take away 3. In that case, and that gives me q is equal to 0.1. And if p plus q is equal to 0.4 and q is 0.1, then p plus 0.1 is equal to 0.4. And I get the p is equal to 0.3. And I can put those in. And there's my values for P and Q. So we wanted to represent events as discrete random variables. We wanted to use mean and variance in the context of discrete random variables and calculate values for the events. And hopefully we've been able to do that. There are some questions on Moodle to try. Please do, and if you have any problems, give me a shout. Thank you very much for watching.